Section: Introduction. In this section, we discuss dataset distillation, DD, which aims to condense a large dataset into a smaller synthetic one while retaining key features for model performance. Since its introduction, DD has attracted significant interest due to its applications in areas like privacy protection, continual learning, and neural architecture search. Recently, methods based on matching have shown promising results in creating high-quality synthetic datasets. We can break down the distillation process into two main steps. First, we extract important information from the target dataset using an agent model, which records various metrics like gradients, distributions, and training trajectories. Second, we optimize synthetic samples to include this extracted information by minimizing the differences between the metrics calculated on the synthetic data and those recorded earlier. However, we reveal that both steps can introduce misaligned information, which can be redundant and harmful to the quality of the synthetic data. We analyze the causes of this misalignment and propose solutions from two perspectives. In the information extraction step, most methods allow the agent model to access all samples in the target dataset, leading to the extraction of information from samples of varying difficulty. Previous studies suggest that we only need information from easier samples when the compression ratio is high, indicating that this misalignment can hinder distillation performance. To address this, we implement data selection methods to assess the difficulty of each sample and use a data scheduler during distillation to ensure that only samples aligned with the compression ratio are used. In the information embedding step, most methods utilize all parameters of the agent model for distillation. While this seems beneficial, we find that parameters from shallow layers provide low-quality signals that are often unnecessary. Instead, using only parameters from deeper layers yields higher quality synthetic samples, as deeper layers capture more complex representations of the data. Based on our findings, we suggest using only the deeper layer parameters during the information embedding step to avoid misalignment. This adjustment significantly enhances performance, demonstrating its effectiveness in aligning information. Through our experiments, we confirm that our two-step alignment strategy is effective for distillation methods that rely on matching gradients, distributions, and trajectories. Additionally, we introduce our novel method, Prioritize Alignment in Dataset Distillation, PAD, which applies our alignment strategy to trajectory matching. Our comprehensive evaluations show that PAD achieves state-of-the-art performance. In summary, we highlight that the distillation process can be summarized in two steps. First, we use an agent model to learn information from the target dataset, and second, we embed this information into the synthetic dataset by matching defined metrics. We also show that both steps can introduce unnecessary information due to misalignment in data or parameters. Section Summary. In this section, we highlight that the two main steps of dataset distillation, information extraction and information embedding, often introduce misaligned information, which can degrade the quality of the synthetic dataset. We propose a two-step alignment strategy that optimizes data selection based on sample difficulty and utilizes only deeper layer parameters of the agent model, leading to significant performance improvements in the development of our method, Prioritize Alignment in Dataset Distillation, PAD, which achieves state-of-the-art results. Section: Misaligned Information Extracted by Agent Models. In this section, we discuss how misaligned information is extracted by agent models. During the information extraction phase, we utilize an agent model to gather data from a target dataset. Typically, existing methods allow the agent model to access the entire dataset, which means the extracted information comes from samples of varying difficulty levels. However, the expected difficulty of the distilled information changes with the information processing capacity, IPC. Smaller IPCs favor easier information, while larger IPCs should focus on harder information. To investigate whether this misalignment affects the quality of synthetic data, we conduct experiments where we remove hard or easy samples from the target dataset in different proportions. Our findings, illustrated in the figure, show that eliminating misaligned data points benefits all matching-based methods. This confirms that misalignment impacts distillation performance, and we can improve it by filtering out misaligned data. Next, we address the misaligned information embedded by metric matching. Most methods utilize all parameters of the agent model to compute the matching metric, which seems to enhance distillation performance by embedding all extracted information into the synthetic dataset. However, since the shallow layers of deep neural networks, DNNs, primarily learn basic data distributions, using parameters from these layers often yields low-level signals that are usually redundant. Our observations, as shown in the figure, indicate that removing shallow layer parameters consistently improves performance across all matching-based methods, regardless of the IPC setting. This demonstrates that relying on shallow layer parameters during distillation introduces misaligned information, thus degrading the quality of the distilled data. We also highlight the success of trajectory matching, TM, methods in recent years. By minimizing the distance between the agent trajectory trained on synthetic data and the expert trajectory trained on real data, TM methods effectively distill key features from the original dataset into synthetic images. TM-based methods optimize the synthetic dataset by aligning two trajectories, one from the real dataset and one from the synthetic dataset. We denote the parameter sequence from the real dataset as the expert trajectory and the parameters from the synthetic dataset as the student trajectory. In each TM iteration, we randomly select parameters from the expert trajectory as the starting and target points, and the student trajectory updates through gradient descent on the cross-entropy loss for a set number of steps. To tackle the information misalignment issue, we propose a method called prioritizing alignment in dataset distillation, PAD, which can also be applied to methods based on matching gradients and distributions, as detailed in the appendix. In our preliminary work on trajectory matching, we follow a two-step process to extract information. First, we train agent models on the real dataset and record parameter changes. The expert trajectory is formed from these recorded parameters. During trajectory matching, we select parameters from the expert trajectory to minimize the distance between the expert and student trajectories, embedding the information into the synthetic data. We also explore filtering information extraction. We demonstrate that using data selection to filter out unmatched samples can reduce misalignment during the information extraction step. Previous studies indicate that TM-based methods prefer easier information and match only early trajectories when IPC is low, while high IPCs favor harder information and match late trajectories. Therefore, we should train early trajectories with easy samples and late trajectories with hard samples. To implement this effectively, we first assess the difficulty of samples in the target dataset. Then, during the training of expert trajectories, we gradually introduce hard samples into the training set while excluding easier ones. Finally, we discuss the difficulty scoring function. Identifying the difficulty of data for DNNs has been well explored in the data selection field. For simplicity, we use the error L2 norm, EL2N, score to evaluate the difficulty of training examples, although other metrics can also be applied. Specifically, we calculate the EL2N score based on the output of a model transformed into a probability distribution. In our study, samples with higher EL2N scores are considered harder. Section Summary. In this section, we demonstrate that misalignment in information extraction and the use of shallow layer parameters negatively impact the quality of synthetic data, and we propose a method called prioritizing alignment in dataset distillation, PAD, to address these issues. We also introduce a difficulty scoring function, error L2 norm, EL2N, to effectively filter training samples based on their difficulty, ensuring that easier samples are used for early trajectories and harder samples for later ones. Section, Scheduler. In this section, we outline the scheduler stages. First, we eliminate the most challenging samples from the training set, ensuring it only contains data that meets a specific initial ratio. Next, as we train expert trajectories, we gradually introduce samples based on their increasing difficulty. Once all data is included, we then remove the easier samples from the target dataset. This removal happens all at once, as the model has already been trained on simpler samples for a sufficient duration. To address misaligned information from shallow layer parameters, we introduce a parameter selection module that masks certain shallow layers during metric computation. We represent the parameters of an agent network as a flattened array of weights ordered from shallow to deep layers. We set a threshold ratio, so the first portion of parameters is excluded from distillation. This ratio should adjust based on the information per class, IPC. For lower IPCs, we need to include more basic information, while for higher IPCs, we can afford to exclude it. In our experiments, we compare our method, PAD, with several leading dataset distillation techniques, categorized into matching-based and kernel-based approaches. We conduct assessments on well-known datasets like CIFAR10, CIFAR100, and Tiny ImageNet, implementing our method based on DATM. We use standard differentiable augmentations and typically employ instance normalization in our networks, unless specified otherwise. For CIFAR10 and CIFAR100, we generally use a 3-layer conv-net, while Tiny ImageNet requires a 4-layer conv-net. We also perform cross-architecture experiments with various networks. Our comprehensive experiments show that PAD outperforms previous matching-based methods across 3 datasets, except when IPC equals 1. Compared to kernel-based methods that use larger networks, our approach generally performs better, especially when the compression ratio exceeds 1%. We find that PAD is more effective at higher IPCs, indicating that our strategy for filtering misaligned information works better as IPC increases. We also assess the generalizability of our distilled data in both low and high IPC scenarios. Our results indicate that when IPC is low, our distilled data surpasses the previous state-of-the-art method on ResNet and AlexNet, while maintaining similar accuracy on VGG. This suggests that our distilled data generalizes well across different unseen networks, particularly at high compression ratios. To validate the effectiveness of our method's components, we conduct ablation studies on the modules and their hyperparameter settings. Our method includes 2 modules for filtering information extraction and information embedding. The ablation study shows that both modules improve performance, confirming their effectiveness in removing unaligned information. We initialize the training set with only easy samples, determined by a specific ratio of the total size, and gradually add harder samples. We control this process with 2 hyperparameters: the initial ratio for training set initialization and the end epoch for adding hard samples. Our findings suggest that a larger initial ratio and a quicker addition of hard samples generally lead to better performance. However, we note that excessively removing difficult samples early in training can negatively impact the distilled data due to distorted feature distributions. Conversely, a balanced approach to adding hard samples allows the agent model to learn information of varying difficulty more effectively. Section Summary. In this section, we outline our scheduler's process for training, which begins by removing the hardest samples and gradually adding easier ones, followed by a single operation to remove easy samples after sufficient training. We also discuss our filtering methods to enhance distillation performance, demonstrating that our approach outperforms existing methods across various datasets and architectures, particularly when managing information alignment and sample difficulty. Section: Other difficulty scoring functions. In this section, we explore the importance of identifying the difficulty of data points to filter out misaligned information during extraction. We compare different difficulty scoring functions, including the prediction loss from a pre-trained ResNet, uncertainty scores, and EL2N. Our findings, shown in Table 4, indicate that EL2N performs the best across various IPCs, so we adopt it as the default measure for data point difficulty, although we note that it can be replaced with a more advanced selection algorithm. Next, we discuss the balance needed when selecting shallow layer parameters. In Table 4, we present results from different IPCs after removing various ratios of these parameters. Our analysis aligns with previous findings. For small IPCs, retaining more low-level information is crucial, as removing too many shallow parameters negatively impacts classification performance. Conversely, for larger IPCs, high-level semantic information becomes more important, allowing us to filter out low-level details effectively. We also illustrate the effects of removing shallow layer parameters on trajectory matching through distilled images, as shown in Figure 4. Without filtering, the synthetic images are cluttered with noise, primarily consisting of basic color distributions and edges, which are not helpful for accurate classification. In contrast, our enhanced method produces distilled images with finer features and richer semantic information, aiding the model's classification accuracy. We observe a clear trend. As we increase the removal of shallow layer parameters, the images become clearer and smoother. We then analyze why masking shallow layer parameters is beneficial from a trajectory matching perspective. Our findings, illustrated in a figure, show that shallow layer parameters have low loss values that fluctuate, while deep layer parameters exhibit higher but consistently decreasing loss values during distillation. This suggests that shallow layers mainly convey low-level information that can introduce noise, diminishing the quality of the distilled datasets. We provide visual evidence of this in Figure 6, where images using only shallow parameters show coarse features. Additionally, we demonstrate the importance of deep layer parameters in Table 5, where we see significant performance drops when these parameters are excluded, especially for larger IPCs. Finally, we discuss our parameter selection strategy, noting a positive correlation between layer depth and trajectory matching loss. We compare different alignment strategies, focusing on sorting parameters by their matching losses and excluding those with lower losses. Higher loss values indicate greater discrepancies, which can enhance the synthetic data. Our results in Table 4 show that sorting by loss improves performance compared to no alignment, but filtering by parameter depth is even more effective. To further validate our approach, we compare our method, FIEX, with BLIP, which also employs a data selection strategy. BLIP uses a utility indicator to determine the usefulness of samples based on IPC settings, pruning those deemed low utility. As shown in Table 5, our method, PAD, outperforms BLIP on IPC 1, IPC 10, and IPC 50, with improvements becoming more pronounced as IPC increases. This reinforces our conclusion that misalignment between IPCs and real data is detrimental, and PAD's selection module is more effective at removing such misaligned information. Section Summary. In this section, we evaluate various difficulty scoring functions and find that EL2N is the most effective for measuring data point difficulty. We also analyze the impact of removing shallow layer parameters on classification performance, demonstrating that while shallow parameters can introduce noise, deep layer parameters are crucial for maintaining data quality, leading to improved performance in our proposed method compared to existing strategies. Section: Generalization to other methods. In this section, we demonstrate that the two filtering modules of PAD can be applied to existing matching-based dataset distillation (DD) algorithms. We combine PAD with a recent DD method called SRE²L, which performs well on high-resolution datasets, to illustrate PAD's versatility. As shown in Table 5, by removing misaligned information from the squeeze stage, we see an improvement in SRE²L's performance for both small and large IPC settings. This reinforces our assertion that PAD enhances the performance of matching-based methods. In the related work, we note that dataset distillation aims to create a smaller dataset that allows models to perform similarly to those trained on the original dataset. Various approaches have been explored, which we categorize into three types: kernel-based, matching-based, and generative models. Kernel-based methods achieve solutions through kernel ridge regression. For instance, FREPO creates a compact dataset using neural feature regression, reducing training costs. Matching-based methods involve agent models that extract information from the target dataset by tracking specific metrics. Notable examples include DC, which matches gradients, and MTT, which matches training trajectories. The distilled dataset is then refined by minimizing the distance between metrics from synthetic and recorded data. Many studies have aimed to enhance the effectiveness of distilled datasets. For example, CAFE maintains the real feature distribution and improves generalization across different architectures. DREAM uses k-means to select key samples for distillation, boosting efficiency. DATM matches early and late trajectories for small and large IPCs, respectively, achieving state-of-the-art results on various benchmarks. BLIP and prune then distill address data redundancy by pruning the real dataset before distillation. PDD introduces a multi-stage distillation process that adapts synthetic subsets based on previous ones to tackle complexity changes during training. Additionally, new metrics like spatial attention maps have shown promise in distilling large datasets. Generative methods, including GANs and diffusion models, can also create high-quality datasets. DIM utilizes deep generative models to capture information from the target dataset, while GLAD shifts synthetic data optimization from pixel space to latent space, enhancing generalizability. Lastly, RDED offers a computationally efficient DD method that rearranges key image patches without needing synthetic image optimization, and SRE²L employs a squeeze, recover, relabel approach to simplify previous optimization processes, achieving success in high-resolution settings with reduced computational demands.